Hi guys, as you can see on my computer here, it's 6:23 in the morning. Anybody else up with me this early? Probably not. I try to still get up early. All right, so we're starting Unit 14, trig derivatives. But our first day here is just going to be what's called differentiability. All right, so read with me. It says, for a function to be differentiable means the derivative exists at each point in its domain. The function has to be continuous if it's differentiable. And remember, to take the derivative means that we can find the slope machine, right? And we can use that to find the slope of a tangent line at any given point. Okay, so I'm going to give you a piecewise function to start out with, and read what I have in the box here. Okay, this is how we're going to do it. It says to determine whether a function is differentiable at a point, which means we can find the slope of the tangent line. Use the continuity test on the derivative. Okay, so my first step is going to be to go back to our limits unit and see if we can find if the function is continuous. So remember the 3 steps to continuity? So the first thing we're going to do is see if a function value exists. So let's see if a function value exists for f of 3. So I have to go up and use the appropriate domain. So the domain I would use for this would be x is less than or equal to 3. So I'll plug 3 in right here, and I wind up with 0. So a function value does exist. All right, now we're going to find the limit of f of x as x approaches 3. Since it's a piecewise function, I'm going to approach from both sides, so I'll approach from the left, and I'll approach from the right. Okay, so let me just erase this, so that's gone. Okay, so when we go back up, for the first part, x is approaching from the left of 3. I'm still going to, though, so look, x is less than or equal to 3, so I'm still going to use this domain for the first one. So if I plug in, 3 minus 3 is 0. Now I'm going to approach 3 from the right, so we're going to be a little bit bigger than 3. So x is greater than 3, so I'm going to use this guy. And when I plug in, 3 minus 3 is 0. So now the limit does exist. Does the function value equal the limit? And it does. So we can say that this is continuous. Now that's just our first step. Okay, it's just the first step in finding if this is differentiable. Okay, the second step in determining whether a function is differentiable at a point is to use that same continuity test, but we're going to use it now on the derivative. Okay, so now we have to find the derivative of the piecewise function. Okay, and that's our last unit, and you just go and you take the derivative of each piece. So the derivative of x minus 3, the derivative of x is 1. Derivative of a constant is 0, so we're not going to write that. It's the same domain. The derivative of 3, which is a constant, is 0. And the derivative of negative x, so 1, right, times negative 1 is negative 1. Decrease the power by 1. So x to the 0, which is just 1. Oh, excuse me. All right, and same domain. Okay, so now that's my derivative, and now I'm going to do the continuity test on that at x equals 3. Okay, so does a function value exist? So I would use this domain, right? That's where x is less than or equal to 3. So my answer is 1. So a function value does exist. Now we'll find the limit. as x approaches 3. But we have to separate that, right, because we have our piecewise function. So x approaches 3 from the left, and the limit as x approaches 3 from the right. Okay, so let's go back up again. So a little bit to the left of 3, so I'll use that first piece of the domain, and I'll get 1. And then x is a little bit bigger than 3, so I'll use the second piece, and I get -1. So now we see that these guys are different, right? So the limit doesn't exist. And now my last piece of this, which I kind of ran out of room, I'm going to go right over here. The function value does not equal the limit. So then this one is not continuous. Right, so if this is not continuous, then is this differentiable at 3? So the answer is no. Okay, so let's backtrack on this. In order to figure out, again, if something is differentiable, you're going to do the continuity test first to make sure that it's continuous, because it has to be continuous first in order to be differentiable at a point. So find out if it's continuous first. Then, if it is continuous, apply the continuity test, the same test, but to the derivative. And if both things work, then it is differentiable. All right, so what I want to do is I want to show you why this happened. I want to show you why it's not differentiable at x equals 3, so you can understand like what the heck that means, okay? And remember, to be differentiable at a point means you can find the slope of the tangent line. Okay, so watch what happens when we graph this, which is kind of neat. Okay, so here's what I did. I made the tables already. So I took from the original function, right, the original function right here. Let me erase some of this stuff here. Okay, so from this original function, I came down and I made a table. Right, so I have x minus 3, and I'm using the values of x is less than 3. So that's why I chose 0, 1, 2, 3. I mean, I could have went further. I could have done -1, -2, right, for the domain. Remember, for graphing piecewise functions, we have an arrow where 0 is because I could keep going lower, and I am including 3, so I put a closed circle. Then for the second part to graph, 3 minus x is greater than 3, so I did 3, 4, 5, 6. You can go more, and then at the 6 you have an arrow, and at 3 it's not included. Okay, so let's graph this, and then it's kind of cool. What happens? Oh, I think I hit the wrong button. Oh gosh, yep. Okay. Okay, so I'll graph the purple one first. So let me just make this like a little thicker. So 0, -3, 1, -2, 2, -1, and 3, 0. Okay, and then I'll graph the red one, and then I'll just do them all in the same thing. So 3, 0. Oh, I forgot to do the arrow. Okay, so the arrow was at 0, -3. So down here, there's going to be an arrow, right? Because it's going to keep going. Okay, 3, 0. There it is. 4, -1. 5, -2. And 6, -3. And then I have an arrow at the 6. All right, and there's my graph. Now let's look. Why? We can see that it's continuous at 3, right? We can see as we approach 3 from both sides, right? We can see that it is a continuous function. But why isn't it differentiable? Okay, so watch. If you were going to try and find the slope of the tangent line at x equals 3, well, let me draw in some tangent lines. I could draw in a tangent line like this. I could draw in a tangent line like this. I could draw in a tangent line like this. Remember, tangent means it only hits one time. There's an infinite number of tangent lines right here. Therefore, you can't find the derivative. can't find the slope of the tangent line when there's an infinite number of tangent lines. And that's because it comes to a point like that. Okay, it would have to be a nice smooth curve in order to find the derivative. Okay, guys, so I made one more here for us to do, and now this one I did write out all the work for, okay, but I'll just talk it through. So it says, is f of x differentiable at x equals 1? So look, if we look at our graph at x equals 1 is going to be right here. I can tell that it's differentiable because it's continuous, right? And we can see there is only one tangent line that we can draw there. But you're not doing it by looking at the graph. You have to do it by algebraically. Okay, so let's go through all the steps that I did here. Okay, first one, is there a function value at 1? So f of 1, if you plug back in f of 1 into the original function, so f of 1 would be where x is, I'll erase all this, erase all that again too so I can use it again. So that's where 1 falls in, right, into the domain. So if I plug in 1, I get -2. Now I'm going to take the limit as x approaches 1. Remember, I'm going to come from the left, I'm going to come from the right. But when I plug back in 1, a little bit bigger than 1, a little bit smaller than 1, aren't I still in this domain both times? So I'm going to get the same answer as -2. So therefore, the function value and the limit equal each other, so it is continuous. Now we're going to do see if it's, we're going to apply the continuity test on the derivative. Remember, we already took the derivative before. This one right here. So we'll just use that again. Okay, so I wrote it down again. And now we'll find a function value. So does a function value exist for f of 1? So if I plug in, I would plug into this piece of the domain. And I would get 1. Now we'll find the limit as x approaches 1, a little bit smaller than 1, a little bit bigger than 1, and again I wind up using the same exact domain. So the limit does exist, and the function value and the limit are the same. So it is differentiable at 1, and we were able to see that by looking at the graph as well. So yes, it is differentiable at x equals 1. Okay, so just because it's not differentiable at one point doesn't mean it's not differentiable at other points. And this is like a common question on the AP. Something to do with this, and it could be multiple choice too. Okay, so let's see. So here's another piecewise function, and I'm setting it up in all parts again for you, just so we can really investigate and look at it. So it says, is f of x continuous at x equals 3? Okay, so let's first see if it's continuous. Going back to our 3 steps of continuity. Let's get a pretty color. Okay, so first we'll see if there's a function value. So f of 3. F of 3 looks like I'm going to be plugging it into this piece of the domain, right? That's where x is greater than or equal to 3. So 8 minus 3 is 5, so a function value does exist. Now let's find the limit of f of x as x approaches 3. Since it's a piecewise function again, I'm going to approach from both sides. Okay, so the first one where x is a little bit smaller than 3, I'm going to plug in right here. So 2 times 3 is 6, minus 1 is 5. We're going to approach 3 from the right, so a little bit bigger than 3. So we'll plug in here. So 8 minus 3 is 5. So the limit does exist, so that's good. And then does the function value equal the limit? Yes. So this is continuous. But remember, as we just saw before, just because it's continuous does not mean that it's differentiable. Okay, so let's check it out. Now we have to apply the continuity test to the derivative of the function. Okay, so we have to find the derivative of the piecewise. So let's go back up. I'll leave it like that so we can see a little bit. All right, so I'm finding the derivative of 2x minus 1. So the derivative is just 2 with the same domain. Derivative of 8 minus x is 8, same domain. Oh, I made a mistake. Sorry, the derivative of 8 is 0. The derivative of negative x is negative 1. Okay. Okay, so let's apply the continuity test. Here we go. Okay, does a function value exist? So I want to plug in to this piece. That's where x is greater than or equal to 3. And we get negative 1, so the function value exists. Let's take the limit as x approaches 3, piecewise function. So we'll approach from both sides. Okay, a little bit smaller than 3, so we'll take out of this piece, and we wind up with 2. A little bit bigger than 3, right, approaching from the right. We'll take from here, we got negative 1. And we can see here that they're different, right? So it does not exist. You can do the symbol, or you can say does not exist. So therefore, obviously, but I like to still do it, the function value does not equal the limit okay, this piece fails, so this is not continuous, so therefore this is not differentiable. Yeah, that's not going to fit. Let's write neither here. Okay, not differentiable. All right, hope that went well. I have a little bit of sniffles, sorry. Oops. Okay. Yikes. Okay, so let's take a look at some theorems, important theorems here. So it says if f of x is differentiable at point C, then it is continuous. So if we know something's differentiable, then it has to be continuous because that's the first step. But the converse is not necessarily true. Just because something is differentiable, it does not mean just because something is continuous does not mean that it's differentiable. And that's like that absolute value function that we saw in the beginning. Okay? And that last one that we just did as well. Oh, we didn't graph the last one. Yeah, let's go up and graph that last one. Sorry. Oh. Yeah, let's graph this one and see why. We didn't do that piece. Okay, so we'll do we'll do, yikes. Okay, we'll do 2x minus 1. Okay, so for 2x minus 1, x is less than 3. So we're still going to use 3, but it'll be an open circle, then 2, 1, 0, and we'll have some sort of arrow, right? All right, so let's go ahead and plug in. If I plug in 3, and we're looking at x is less than 3. So if I plug in 3 right here, 2 times 3 is 6, minus 1 is 5. If I plug in 2, we'll get 3. If I plug in 1, we'll get 1. And if I plug in 0, we'll get negative 1. So that's for that piece. We can go ahead and graph it if we want to. 3, 5, 1, 2. Oh, but there's an open circle there. Let me do that again. 1, 2, 3, 4, 5. Open circle. All right, 2, 3, 1, 1, and 0, -1. And then we have an arrow at this part. Okay, and the other guy, 8 minus x. X is greater than or equal to 3. So I like to still make the table like how it would really look, you know? I think I'm just going to go up to this one. I don't know why I drew it like that. That was silly. Sorry, 3, 4, 5. All right, so we plug in 3, we get 0, and then we're plugging into this piece now. Yeah, okay, I'm having a moment. Okay, all right, so the domain is x is greater than or equal to 3. So 3, 4, and I'll just stop at 5. And now we'll replace in. So we're replacing in here into this function. So we get 5, 4, and 3. All right, and let's go ahead and graph those. I think I need to move this graph over now. Yeah. Okay, so 3, 5, 1, 2, 3. So 3, 5. Now this hole gets filled by this piece. 4, 4. And 5, 3. Sorry, it's hard to graph on this. I think that's 4, 4. And 5, 3. Okay. An arrow at the end of that one. All right, and again, we can see at x equals 3, y is not differentiable, right? Comes to a point like that, and there's an infinite number of tangent lines. Okay, we went through our theorems again. What is the most important thing here? If it's differentiable, it has to be continuous. Okay, yikes. Okay, if it's differentiable, it has to be continuous. But if it's continuous, does not mean that it's differentiable. Alrighty, let's check out number 3. So we'll do one more like this. In class, I was going to do this as a 2-day lesson, so that's why this is definitely a little bit long. Okay. So we have a piecewise function. I want to know, is it continuous at x equals 0? So the first thing we'll do is we will find out if our continuity step test works. So we'll find if there's a function value at 0. So I would plug into this piece of the domain. We get 0, so that works. We want to know what the limit is as x approaches 0. Piecewise function will approach from the left, will approach from the right. So a little bit smaller than 0, we'll plug into this piece. 0 squared is 0. Second piece, x will approach from the right, so a little bit bigger than 0. 0 squared 0 plus 1 is 1. So we can see right away here that the limit does not exist. So we know that the function value does not equal the limit. This piece fails, right? As does this one. So this is not continuous. As soon as it's not continuous, we know that it's not differentiable. We know. But do me a favor. I want to show you something anyway. So can we let's just do the next step, because I want you to see what happens here. Let's just do this next piece. Even though we could stop right now, but I just want you to see something. Okay, so let's find the derivative. So the derivative of x squared is going to be 2x. And the derivative of x squared plus 1 is also going to be 2x. And now let's do our continuity test on this and watch what happens. Okay, so we get our function value. Oopsie. Our function value does exist, right? If I want to find f prime of 0, I would plug into this piece right there, 2 times 0, 0, so that works. Now what if I want to take the limit as x approaches 0 of f of x? Approach from both sides. Okay, so a little bit smaller than 0. We'll plug into this piece. Obviously, you can see we're going to get 0, 2 times 0, 0. We're going to approach from the right, a little bit bigger than 0, 2 times 0, 0. So we can see that they're the same, right? This does exist, right? So this is 0. And we can see that the function value does equal the limit. Right, so here we think that it's differentiable, and that's what I want you to notice. This appears differentiable. But is it really differentiable? But it's not, because the limit didn't exist. So this is why you can't just jump to this step of just finding the derivative and applying the continuity test on the derivative, because it can appear that it's differentiable, but we already know that it failed because it wasn't continuous. So that's just something I wanted you to see. But let's graph it and take a look at what happens as well. I'll move this down so I can make tables. Okay, so for x squared, we have x is less than or equal to 0. So 0, -1, -2, -3. At 0, it's included, and there's some sort of arrow here. So let's plug in for x squared. So 0, 1, 4, 9. Let's make our second table, and then we'll graph everything. So x squared plus 1. And the domain we're using for this one is x is greater than 0. So 0 with an open circle, 1, 2. I don't think we're going to be able to fit higher than that there, so I'll just stop anyway. So 0 squared, 0 plus 1 is 1. 1 squared is 1 plus 1 is 2. 2 squared is 4 plus 1 is 5. Okay, so let's go graph these guys down here. Okay, so we got 0, 0, -1, 1, -2, 4. I don't have room for the other one. But we can see and we can tell, we know that this is a part of a parabola there. And then let's graph the blue side. So now I'll do this one in blue. So we have 0, 1, and that's an open circle. Let me just do this. Okay, so 0, 1 is an open circle. 1, 2, and 2, 5. And we know that that's parabola-ish as well. An arrow, oh, the arrow was at the end here. All right, so looking at that, we can see that at 0 it is totally not continuous, right? This is not continuous as we approach from the left and the right. We don't land in the same spot. But it does appear to be differentiable at 2, right? Because we were able to find, we were able to prove that it was it appeared that it was differentiable because it passed this continuity test here. Alrighty, okay, one more. So this is a multiple choice question. But it does still require a lot of work. It says, given the function below, which statement is true at x equals 3? Okay, so we have our piecewise function. Let's read through them all. It says continuous but not differentiable. All right, so obviously we'd have to do some work there. Differentiable but not continuous, well, that's the one that we know can't happen, because if it's differentiable, it has to be continuous. Both continuous and differentiable, neither continuous or differentiable. Okay, so that means we got to do all our steps. So why don't you guys pause the video and why don't you do the whole thing out, and then you can replay it and see if you get it right. Okay, go ahead. Okay, so I'm going to do the 3 steps to continuity on the function itself. So let's see if a function value exists. Now I'm going to do it at the point that they're sharing, okay? That's what I would have to check out and see. So is it continuous at that point they're sharing? So f of 3, so if I'm going to plug in for f of 3, I'm going to plug into this piece of the domain. 6 times 3, 18, minus 9 is 9, so a function value exists. Let me see if the limit exists. As x approaches 3, we'll approach from the left. We'll approach from the right. Okay, so x a little bit smaller than 3, we're going to get 9. X a little bit bigger than 3, we're going to get 9. Okay, so this looks good. The function value does equal the limit. So therefore this is continuous, so first step is done. Now we'll go ahead and find the derivative and apply the continuity test on the derivative. Okay, so the derivative of x squared is 2x. The derivative of 6x minus 9 is 6. Okay, let's find if a function value exists. So we'll plug into this piece of the domain, right? X is greater than or equal to 3, so we get 6. Let's see if the limit exists. So we'll approach from the left. We'll approach from the right. A little bit less than 3 means we're plugging into this piece. We get 6. A little bit bigger than 3, we're plugging into this one. We get 6. These guys are the same. That's great. The function value does equal the limit. So therefore this guy is differentiable. Okay, so it was continuous, it was differentiable, so my answer is choice C. Okay, so that was a long lesson. And then for homework, I'm going to have you guys just do, oh goodness. Okay, so this next one right here, and you could do just number 1 for homework. Okay, you don't have to do the other ones, just practice one time for me. All right, guys, great job. Replay the video and watch again if you need to. This is really important stuff. All right, bye.